Math 1343, Week 10, Video 5, Calculating Variability. So when we were looking at the illustrations of the samples from different data sets and saying, well, this provides stronger evidence that the population means are different because there's less overlap, and then we blamed it on variability between groups or variability within groups. Well, that's nice and all, but we need these things to be numerical, measurable, quantifiable, if you will. And so in this video, we're going to talk about how to calculate all these different variabilities. There's three types of variabilities we can measure for a data set. Don't bother me to not pluralize that. There's three types of variabilities we can measure for a data set consisting of samples from multiple populations. Number one, of course, is variability between groups, which is based on how far apart the groups are from each other. Number two is the variability within groups, which is based on how varied each individual group is, so how wide each group is. And then there's what's called the total variability. Now, all three of these have formulas, and I'm going to share them with you, but I don't want you to get intimidated. Variability between groups is abbreviated SSG. If you ever see SS, it's short for sum of squares, which means we're adding a bunch of squares. The formula for SSG is the sum of the sample size, which is the NI, times the square of the deviations of each sample mean from the grand mean. I don't think we've talked about the grand mean yet. I know I snuck it in the Excel spreadsheet, so let's go take a look at that real quick. Let's see, we'll have to go to the front page. There we are. When we talked about the sample size, mean, and standard deviation for each individual sample, that's precisely what it was for each individual sample. But when you're doing multiple populations and multiple samples, there's also a concept called a grand mean, a grand standard deviation, and a grand sample size. Basically, it's the mean, standard deviation, and sample size if you took all of your samples and treated it like one gigantic sample. So in other words, if we lost track of the batting position for these numbers and just look at it as one gigantic sample, the grand mean would be the average of all those. Grand standard deviation would be the sample standard deviation of all those. And of course, the grand sample size would be 270. Now, if you think about it too much, you might start thinking, well, isn't the grand mean just the average of the means? And the answer is only if all the sample sizes are the same. And isn't the grand standard deviation the average of all the? No, it's not. But the grand sample size is the sum of all the sample sizes. There were 9 samples of size 30, 9 times 30 is 270. So within these formulas, we'll have variables that refer to specific individual samples. You'll recognize them because they'll be subscripted, and variables that refer to the grand sample. So let's go back to the formula and take a look at it. For variability between groups, for each sample, we're going to take its sample mean, subtract the grand sample mean, square that, and then multiply it times the sample size. And then we're going to take the sum of all those. Now, I'm not going to write every single add-in, but for example, if we go back to the first sample, the first sample size is 30, the first sample mean is 181.3, the grand mean is 155.7. I'm going to do myself a favor. I'm going to take a picture of this so that I don't have to text a picture, so I don't have to go back and forth between everything. That picture, and not have to bounce back and forth between the whiteboard and the spreadsheet. So let's go back to the whiteboard, and then we'll get this started. All right, so the first sample was size 30. The first sample mean was 181.33, but the grand mean was 155.70. And that difference would get squared. And that is the calculation from the first sample. From the second sample, its sample size was also 30. Its sample mean was 179.73. And the grand mean was still 155.70. Square that difference, plus. And you have to do that once for each sample. Now, this one had 9 samples, so there would be a total of 9 addends, if you will. The last one still had a sample size of 30. Its mean was 113.13, and the grand mean is still 155.70. That would get squared. Now, what does all that equal? Well, there is a way to do this in Excel, and since I'm going to do it in Excel, I might as well let you watch me do it. But let's just move all this stuff down for a minute. Here. All right, so for each of these, I need to calculate sample size times the mean minus the grand mean. We'll just say G over grand mean. All right, so this is going to equal 30 times, open parentheses, that mean minus, I'm just going to type 155.70 since it's going to be the same grand mean for each one. Now I can just copy and paste that all the way across. And that's not right because those should be negative. I left out the square. Try that again. 3 large numbers. Except right there, that one's pretty small. That's because the mean here was very close to the grand mean. So if we take the sum of those, that's going to equal the sum of these. And it looks like we get about 118,956. 118,956. 118,956. As you can tell, it's a rather lengthy calculation. If we only had like 3 samples, 3 populations, it'd be a lot more manageable. Now, for variability within groups, we actually have a couple of options. The abbreviation for variability within groups is SSE, and E is for errors. And there's actually 2 ways to calculate it. One is to calculate this sum. Now, this sum takes a long time to calculate because what this X represents is a single value. And since we had 9 samples of each with 30 values, there would be 270 values. What you do is you take each value, subtract it from its sample mean, square that, and then add them all up. But this would be 270 terms because that's our grand sample size. So for, just to make sure you understand what I mean, for each individual number, let's go back to the spreadsheet. For each individual number, like this 186, which came from the first sample, then you would have to subtract that 186 minus the first sample mean, square that, and do the same thing for the other 269 numbers. That's a little bit unreasonable. But you may have noticed that there's another formula. This formula says you have to do this sum once per sample. So for each sample, you would subtract 1 from its sample size, multiply it by the square of its standard deviation, and then take the sum of all those. The reason the first formula exists is to kind of point out that we are looking for variability within each group by comparing each data point to its sample's mean. But we can do it a lot easier by just using the second formula. So if we started the second formula, it would go something like this. The first sample size was 30. They were all 30. So 30 minus 1. Then times the square of the first sample standard deviation, which was 17.82. So 17.82 squared. And then we would do that all the way down to the 9th sample, whose size was also 30, and whose standard deviation was 16.31. So it's still a lot of calculation, and I still think it's worthy to go into Excel and have it do the dirty work for us. So let's clear out this stuff and tell it what we wanted to calculate. Here we want to do n minus 1 times the square of the standard deviation. That's not a formula, that's just saying this is what this row is going to represent. All right, so equals, parentheses, sample size minus 1, close parentheses, times the standard deviation squared. And copy and paste that all the way across. Make sure it looks good. And we'll take the sum of those by saying equals the sum. And it looks like we get 61,365.2. 61,000. Where's my screen? 61,365.2. All right, so that was kind of a cumbersome calculation. But we got one more, the total variability. Now, as the total variability's name implies, it's the sum of these two. Now, why is that useful? Because when we do our ANOVA calculations, we only need two of these three because we can either add or subtract to find the third. So keep that in mind. Now, we could calculate that here, but there's also two other formulas for it. One, for the total variability, you would pretty much ignore the fact that there were different populations, and you would take the sum of the squares of the differences of each individual value from the grand sample mean. So we don't have 9 samples of 30 each. We got one giant sample of 270. That sum's a little bit cumbersome. Now, I spared you the algebra, but that sum is just equal to this. Not even a sum in its own right. The grand sample size minus 1 times the square of the grand standard deviation. So we could calculate the total variance really easily by taking the grand sample size, which was 270 total observations minus 1, times the square of the grand standard deviation, which was 25.89. 25.89. And if we multiply that all out, here, I know it's, where's my calculator? You get 269 times 25.89 squared. And that gives us, we'll take it to the nearest whole number, 180,308, actually rounds to 309 because it's 8.57. Now, does that jive with the first part of the formula that says it's just the sum of the previous two variabilities? Well, we can check that real quick by just going back a couple of pages. 61,365.2 plus 118,956 equals, and the sum that I got was 180,321.2. Off by a little bit more than I expected. I'm going to attribute it to rounding errors because I'm not going to try to go back and do damage control. But the point I'm trying to make is when you do the total sum of squares, excuse me, the total variability, that's what SST stands for, total sum of squares. There's actually 3 ways to get it. One is to add the first two variabilities. Draw. 2 is to do the formula where you add one thing per observation, but that's usually cumbersome. But the third and easiest way is to do this, provided you have that information. Now, if you're panicking about having to calculate this, which really wasn't that bad, it's just the last formula, this, which is a sum involving 9 terms, because there were 9 samples, or this, which was also a sum involving 9 terms or 9 samples, don't panic too much. In the homework, you'll probably have 3 populations and 3 samples at most, maybe 4. But the calculations really aren't all that bad. And it gets even better. In some problems, you're told what SSG, SSE, and or SST are equal to. You're given 2 out of the 3. You can use this last relationship to calculate the missing one. And then we do what we're going to do with it, which you'll see in the next video.